This conference will now be recorded.
Randy, are you going to be showing slides or your screen or something?
It's gonna be a mix, so I definitely need screen sharing. I've got slides and then I've got a fair number of interactives I just wanted to demo. So
Okay. And normally we have other people managing that, so I need to figure out how to hand over screen sharing to you.
mhm.
Um, so I think you're in control now.
Yeah, it looks like it. Let's see, and I've got 3 monitors, so I gotta make sure I pick the right one here. Okay, hopefully you're seeing Saturn and about to see some PowerPoints.
That's what we're seeing, Saturn.
Okay. Let me start this. Where is it? There it is. Okay. So obviously we've not exactly got a huge crowd. So, if anybody's got any questions along the way, feel free to pipe in. I'm really mostly planning to do kind of a show and tell. And certainly if there are some things that are of more interest to people than others, I'm happy to diverge more in that direction. I've got a lot of things I could show. I think I'll just go for a while and then cut it off because I know this is a group that likes to chat about stuff. So I could easily go on for a couple hours on this. So I'll just have to draw it to a close at some point, partway through the hour. Um, so as I mentioned, I'll mostly be trying to sort of demo some simulations we have. Most of them are computer based, but some of them are more hands-on things. So I've got some slides to kind of illustrate those. Um, let's see, I'll do just a little quick introduction of myself and NCAR and the UCAR Center for Science Education where I work, and say a few words about how modeling is called out in the next generation science standards, which is a lot of my motivation for the sort of why of this approach, and then a bunch of demonstrations of various simulations, games, interactives of relevance in the earth sciences, and particularly for climate and energy kind of issues. I think more on the climate side, but there are a few things here that I've got that relate to energy as well. And I think that's the gist of it. Um, I started off in astrophysics and then got into aerospace engineering, and then somewhere along the way got more and more interested in STEM education, got my PhD from Michigan State. I've been here in Boulder at NCAR for just over 15 years. I'm technically on the UCAR side of the fence. I'll make a brief mention of the distinction, but for most people, it's not really a distinction you should worry about. My main passion is developing educational simulations and games. I do stuff with online courses and do a fair amount of writing of web pages and do quite a bit of teacher professional development, both face-to-face and online. Um, I'm guessing most of you are somewhat familiar with NCAR, but in case somebody isn't, it's a large climate, atmospheric science, weather research lab in Boulder, Colorado. It's one of the sort of premier places of that sort in the world. UCAR is kind of the oversight and consortium of universities that interacts with the national lab. So I'm technically in UCAR, but I'm situated right next to NCAR scientists. So it's really kind of a nonsensical distinction to most outsiders, but our group is technically called the UCAR Center for Science Education, or UCAR SciEd. So consider UCAR and NCAR synonymous for most of your purposes. We do run a supercomputing center at NCAR. It's actually up in Cheyenne, Wyoming now. It used to be in the building I was showing in the last slide in Boulder, but it kind of outgrew that. But anyhow, because of that, there's a lot of interest in computing, computational thinking education and modeling here. NCAR also is sort of the caretaker of some community climate and weather models. So modeling's a big part of what's done here by the scientists. So it's pretty fair game for us to get involved with that as educators affiliated with the institution. I'm going to quickly just flip through a few slides here. I developed these for a webinar I did for the NOAA Planet Stewards a couple of months ago, and it was for elementary education and went into a fair amount of like what exactly is a model, because it's a word we use in a lot of ways. So I'm just going to briefly mention that these slides are available online. You can look through them a bit more. This was sort of what I gleaned from some of the NGSS writings of just the distinction they made between mental models, which is what is in somebody's head, and a conceptual model, which is more of a scientific model used to communicate with others. And examples they talked about were things like diagrams and scale models and physical replicas and mathematical representations. And then the main thing that I'm going to get into here today is computer simulations. I think I'm going to skip through several of these slides. If you're interested in sort of a summary of some of the places that NGSS references models and what they have to say about them, this is a little bit of a summary of that. So I'm going to skim ahead of this. I don't think it's quite as relevant here, or it might be relevant to some of you, but it's not really the main thing I want to get into. But just be aware that if you want to get into a bit of what is meant by models and different types, there's some slides here that you can reference.
And Randy, I personally would back up. What you're doing is right. We're interested in. I am certainly interested in what you do. We do our homework, and we do have some good background. But you're important, and hearing about you is great. So, what
Thanks.
you do.
I'm going to jump into the simulations now. I guess a couple of points to me. One is, I think it's really important for students not to merely learn about models, but to behave like scientists and thus run models, develop models, modify them, that kind of thing. I think there's an important topic of sort of the constructing models or constructing depictions of complex systems, concept maps and things like diagrams of water cycles and that sort of thing, I think are also important for students to do. So I don't want to minimize that. That's not the main emphasis on some of the things I'm going to be showing, because I think just having arrows between things is helpful, but sometimes the sort of quantities around those arrows are really important. So you really need either mathematical or computer-based things to show that a certain system blows up because this one aspect of it is really dominating everything else, or things like that that merely just sort of the connections don't always show. So that's my little soapbox about why I think these are an important element along with many other things, and that sometimes just running models, simple simulations is really important, as well as having students build their own sort of conceptual models. I also really like to emphasize when talking about modeling with teachers, this quote from George Box that all models are essentially wrong, or at least limited, a lot of people prefer to say, and really talking with students about what the limitations, where the models aren't exactly like reality, is an important part of the whole process. NGSS has a number of things to say about that as well. Okay, and I'll also mention, and Jim, you'll like this because I was actually, I've been thinking about this a fair amount, the pairing of these computer simulations and that sort of model with physical hands-on stuff is something I'm pretty intrigued by, and I think has a lot of power. I've only started to explore the literature on that, and I don't think there's a lot yet, but the notion that, physical manipulating an actual tree ring sample, a tree cookie or a core or something or just doing that hands-on stuff is really powerful and important. And often there are things that you can do in a simulation that couple with them that you just can't do with the real life stuff, either because of danger or time frames or access because of needing to go out in the field and so forth. So let's see. Another example of, along with the sort of tree cookies kind of stuff that I'll try and get to here, the FET collection at University of Colorado has a nice glacier simulation, and some of you may have seen some of these flubber, glacier goo kind of things like the slide on the left shows. I think that's another interesting sort of pairing where you can do the physical stuff and do the computer-based stuff and get a lot out of the combination. Without further ado, I'm going to just jump over and demo some things, and we'll see how far I get. And I'm just going to keep track of time here and show some of these in hopefully a little bit of a coherent order. And let me drag this onto the screen. So I'm just pulling over a web page now, and I'll try and remind myself where the chat is and paste URLs into that as we go along. Let me do that. This first one, some of you may have seen before, so I'll go over it kind of quickly because it's been around for a while. There's the URL in the chat. It's basically about the idea that there's fairly simple calculations we can do to predict approximate global temperature based on human carbon emissions going out the coming century. So you can do a sort of what if. We've got a historical plot of CO2 emissions. We're up to, I think I need to update this with the most recent data. We're up to a bit over 10 gigatons of carbon emissions per year. So that's what the trend of these triangles is showing. We can also see the carbon dioxide concentration in the atmosphere, and as you know, we're on the order of 400 parts per million, a little above that now. And then the third thing we can see on this graph is temperatures, which wiggle a bit more. The average global temperature, because of things like El Niños and other different effects that cause them to change a bit more from year to year, but the trend is upward like the other two. And the idea behind this is you can do what if experiments saying, well, let's see if emissions next year or in the next 5 years go up a little bit and go up a little bit more. Let's see what's going on with concentration. Not surprising, it's continuing to go up, and temperatures, not surprisingly, continuing to go up as well. We can do the business as usual kind of scenario where we keep rising throughout the rest of the century. We can do something where it sort of levels off if we start using more green energy, less fossil fuels in a few years, or we can even have a scenario where it goes back down. That's the most interesting one because it's kind of counterintuitive to a lot of people that if the emissions start going down, everything else should, of course, start going down. So I'll go ahead and move this into play mode. I'll go up a little bit more. I'll let it level off a bit and then start going down. And this is where people kind of expect that the amount in the atmosphere should go down and the temperature should go down. And that's sort of the aha part of this. If you have them run the other sort of variants of this and then come to this point and wait, it's still going up even when the emissions are going down, it sort of brings on the urgency of trying to cut emissions soon. So there are some things on here where we can show the recommended 2-degree above pre-industrial limit to try and use that as a value to keep under, and various other aspects you can play around with the scale, but that's the gist of that one. As I mentioned, a related thing, and other groups have done similar versions of this analogy of a bathtub of the atmosphere is kind of like the tub in terms of the amount of carbon dioxide in it. The emissions from all sources are the flow in, but there's a drain pulling it out. And under pre-industrial natural situations, for the most part, the amount in and the amount out in any given year was about the same, and the level in the tubs stayed the same. And of course, you can then go on to, oops, let me go to that one. Let's see, did I get the right one? Yeah. But we've gotten into the industrial era where we're putting more into the bathtub than is going out naturally, and so it's filling up. And the analogy further goes that if you turn the spigot back down some, it depends how far you turn it back down to whether the water level keeps coming up. If you only turn it back down a little bit, you still continue to fill the tub. So as I mentioned, other groups have done that sort of thing, but we thought we'd throw one in there to sort of complement what we were doing with the simple climate model. I'll show one more related to kind of those concepts. There's a simple energy balance kind of calculation that one can do. It's really a little bit of geometry and some algebra that gives you the sense of what the temperature of a planet would be actually, the temperature of a planet would be based on its albedo and its a different distance from the sun. A lot of textbooks will have this as sort of a introductory thing about getting a sense of what the temperature of a planet might be. And then for Earth in particular, it's a segue into why a certain amount of greenhouse gases are good, because otherwise our temperature is really cold. So we can play around with the sliders on here and make the planet brighter, and it reflects away more of the sunlight and gets colder. We can make it darker and bring the temperature up a bit, but we still are on the order of freezing, even with a very low albedo. You can actually pick from certain surfaces based on the known albedos of them. So we can have a planet completely covered by clouds or one completely covered by asphalt. And we can look up the sort of range of values that are relevant, because most of these have sort of a range. We can also do the faint young sun paradox and crank the sunlight down to 70% of what it is today, and then it's really hard to get an even close to temperate planet. And then one fun part of this is the math behind it. If you have younger students or people who aren't going to be as keen on the math, you can keep that hidden and just play around with the visual aspects. If you really want to reinforce the math with, say, older students or more sophisticated ones who maybe have done some of the hand calculations themselves, we've got the equations shown, and they update as you drag the sliders around. So that's, I guess, the main features of those couple that I wanted to show. And I'll pause briefly to see if there are any comments, questions while I pull something else up.
So Randy, question. Jim Callahan here for where it's saying caller 1. We love your stuff. I love your stuff. We've seen it before. This is fantastic things. I don't want to bore people with how we want to use it, but essentially it's part of videos that depict the hands-on part, making that transition. What do you like on attribution? We have no problem with attribution in the comments, captions on the bottom, in voiceover. Can we link to you or have you integrate you into a video? Or how do we go about linking to you into a video with it, and what do you want with attribution?
Yeah, I mean, NCAR is pretty much about freely disseminating stuff. I mean, everything I've done here really is owned by NCAR or UCAR. So it's really their policy, and it's pretty much, I mean, I like, as a courtesy, if people make sure and include URLs to our stuff so that they kind of point back to the original to come play with it. But really, it's pretty freely available to be used. I think if any of it gets involved with commercial stuff, then the rules might be a little different. But I think they're still pretty flexy, and so yeah, we could talk details. But in general, it's in general we want to sort of give it away. So
right, and that's very green light territory, and absolutely, it would be more like a clip to see. Okay, this is what it's like. Now go there yourself. I mean, to send people to you, but to have a clip to say, this is a fantastic resource that goes into this in a different way than what we do. So,
yeah, and we have segments of some of these that I've done because I knew I wouldn't have live internet at conferences or different, situations where I couldn't demo them live. So I do have video clips of a lot of these things, of sort of the baseline demo of them. So that would be relatively easy if we hit on the thing that you needed.
Yeah.
Cool.
Thank you.
I'll show you a newer piece that we've done that probably hasn't been seen by most folks in this group. With teachers, we've frequently encountered the notion that they want to get at least a bit into paleoclimate kind of stuff, because that helps them justify to their students that what we're predicting for the future is based on things that we've observed in the past. So tree rings is clearly very accessible paleoclimate proxy. Ice cores, I guess, is probably the best known of the other ones. But tree rings are pretty easy for people to gather up those physical samples and have, kids actually deal with something that's in their own environment that they've encountered and that sort of thing. So we made a little tree ring simulator. The basic idea is that you're given half of a tree cookie, and you're trying to match the pattern by year assigning the climate values. So we start off saying, well, let's just grow a new ring. Okay, that one seemed to fit, so it's a match over here. If we grow another one, nope, that's not quite right, so let's take it back off. Maybe that was a drier year, and we'll try grow a new one. Nope, that didn't fit either. So let's try a wet year and grow a ring. We're good there. I happen to know the next year is normal conditions, so we'll go that. And then I think it's dry after that, and we'll go that. And so on. And we try and just make sure that we match this and, take rings off if they're not the right match, but then add in ones. And we build up a graph of the climatology as we go across the bottom so that we can see once we eventually build the whole thing. Let me see if I can remember what the order is here. Gonna get another wet one. Whoops. New ring. Nope. Well, anyhow, you can see that if you build up the graph, you could ask questions then of, were there any long periods of drought, or was it normally wetter or drier, or kind of just normal conditions in this place, and so forth. We have other levels of this. So we played around with moisture there. We now do the same sort of thing with temperature. Again, trying to match the rings on the sample. Let's see what that one is. And again, you can ask questions from the bar graph of students. And then we make it really complicated where we have both factors playing in, and then it gets pretty tricky to actually get the right values, but I've seen kids be pretty diligent and work through it. We have a couple of case studies in this one. We have a period where there's a long drought, so you explore that and try and figure out what that's all about. And then we have one where there's a gradual warming trend, and so you can look at that. I'll mention that this one has been done in using HTML5 technology, so it's the newer stuff that can be run on iPads and other tablets and so forth. Some of our other things are still in Flash. We're in the process of converting them over. I think within the next year and a half or so, we should have all of them done. We've got a new piece. Yeah, go ahead.
The link for that one in the chat.
Oh, yeah, thank you. Thank you for the reminder. Let's see. And actually, there's a couple others that I showed. I should throw those in. And the energy balance one.
Yeah, while you're doing that, I'll mention that Ingrid Zabel and I are working on replacing our climate and energy exhibit at the Museum of the Earth. And one of the things that we've talked about, I'm not sure if we're going to be able to swing it or not, but is looking at tree rings and ice cores kind of together and coming up with some kind of virtual pointer to go across years in the different proxies.
Oh, that'd be cool.
I don't know if we're going to be able to pull it off, but we'd love input on how to do that. And I think this would be a great, support activity that we could point to for teachers coming through.
Yeah, I've been hoping to do a companion ice core one. It would have to be a bit different in exactly how it would work, but it would be really nice to have a couple of different proxies and make that connection. We did do some work. The folks here who run our exhibit space up at the Mesa Lab installed a new climate exhibit about a year and a half or so ago. And one of the things they did was have a cast made of a simulated ice core out of like acrylic or something like that.
Yeah, we've actually got one of those already in
the okay.
Do a better one actually.
Okay, yeah, and I can, if you're looking, drop me a line because I can put you in touch with Becca who did that.
Yeah, and I think I don't want to derail us, but I think Ingrid and I will see if we can do a sharing of our ideas on a clean call in early 2019.
Cool. Okay, we've got another piece on the, whoops, it's jumping around, on the tree ring front that's in production. We're working with some folks in the UK at the Royal Meteorological Society who are interested in, they've got a whole curriculum they're building on, oops, let me go back to that, on dendrochronology. They're working with a university in Wales that does research along those lines, and they're building a curriculum that they think will fit in at a couple grade levels at a new UK science curriculum. Anyhow, with this one, the idea will be that we're trying to get cores from different, like from a live tree, from a down tree, and then from an older sample, and then get overlapping chronologies that we can then build up a longer chronology. So we do that by simulating some cores. So the idea is that these are meant to be tree ring cores. We need to make them graphically a little prettier, but you get the idea. And if we line them up, so this is the most recent from a live tree. This would be an older one from a tree that had, died 20 years ago or something, but had not decayed yet. And let me see, there's the alignment on that one. And then this might be a beam from a log cabin or a ship or something that was older still. And in reality, you wouldn't exactly match up the specific samples. It would be from a variety of samples and averaging, but conceptually the idea here is that we line them up, and then up pops the temperature chronology that goes along with that. And then we're going to do some more stuff related to putting some hotspots on this that you can click on to find information about eras where it was colder or warmer or what was going on around that time. So,
and can you stick that in the chat too?
This one we don't have quite published yet. So even though I can show it to you because I'm logged in, it wouldn't come up for people. It's still in production. So
how is, Randy, this is Tamara, how is the temperature record developed from the tree rings? Is there is it an analysis that was done by scientists that then you're just showing, or is there some other way that you're producing the temperature record?
yeah, so we're actually doing it in reverse. The temperature record, well, so this group in Wales that the UK folks are working with actually does some sort of a carbon dating style of approach to their tree ring work. So they're not actually looking at the tree ring thicknesses, they're looking at the carbon isotopes in them and then extracting temperature data from that. In the process, they're building up a temperature chronology for this particular region in Wales. And that's what they're actually supplying. So we're really kind of backing out the tree ring widths from that. We didn't actually get data on tree rings actual widths and then compare them with actually separately found temperature data. So it's a little bit of a fudge. We're really using the temperature data that they found via tree rings.
So you're just using statistics to determine what the tree ring widths probably were for a given temperature?
Yeah, basically we just have a mapping that if it's,
Right.
13 degrees, it's this width. If it's 14 degrees, it's that width kind of thing.
Okay.
Yep. So it's kind of using real, I guess the temperature data is real data and it was extracted from tree rings, but the tree ring widths in this are constructed from the data.
Okay.
Let's see where we are time-wise.
Let me ask one more question about that.
Sure.
This is Karen Holweg. Is there any evidence that trees are like some other plants, that the level of carbon dioxide and the temperature changes the growth pattern, that it's not just intuitively a straight line?
That's a good question. I know what the real scientists do when they do tree ring research is they find trees. They don't do ones that it can be different factors that are influencing it. So they find ones that are right on the edge of a very dry environment, that the moisture is absolutely the limiting thing by far in the growth rate of the trees there, so that if there's a slightly wet year, they grow like crazy, and then most of the times they don't. Or they will find trees that are growth limited by being in a cold environment, so either far north or near tree line kind of thing up in mountains. And there they're dominated by the temperature, so they don't have sort of that confounding a couple of different things. I'm sure if you get even those couple of different factors involved, it gets nonlinear. I don't know about, I'm trying to remember, I heard something about increasing levels of CO2 and whether that was affecting tree growth. I kind of have a sense that I heard something that wasn't that much of a factor, that the amount of CO2 in the atmosphere wasn't the thing. It's just the temperature changes their growth. But I could be wrong on that one. I just have a vague recollection.
And Jim Callahan, one thing I'd put in too of in some of the science, this goes back about 20 years, I think. So absolutely, trees are affected, and there are studies of it, which you're pointing to. What gets interesting is if you compare the different types of plants. So there might be trees, there might be grasses, there might be what we call crops. In general, one of the types of plants that grow the most because of extra CO2 are what we generally characterize as weeds. So that's one thing to consider from an economic or an agricultural point of view. Yeah, if you want to grow more weeds, you want more carbon dioxide. If you want to grow more trees, you probably want to cut down on your carbon dioxide because the climate change outweighs the extra carbon dioxide helping them to grow.
And are you saying wheat or weeds?
Weeds, WEEDS.
Thank you.
Basically, the plants that people don't like actually are the type of plants that grow the most with extra carbon dioxide.
All the invasives we're concerned about. Yep, got it.
I'll say the things that have more characteristics of weeds. So yeah.
Thanks.
Yeah. Mm-hmm.
And I guess along those lines, one other thing that I've heard is, because you do hear people saying, well, if we've got more carbon dioxide, all the plants will be better and that'll be great. And I guess one thing that I've had pointed out to me is that things like phosphorus and sulfur and all kinds of other things become limiting nutrients for plants pretty quickly as you increase carbon dioxide. So it's not super likely to make most plants grow a lot more. So that's kind of debunking that that claim that some people might make. Got a sense I should probably show you just a couple more things and then mostly wrap it up for the day. I think I'll be a little whirlwind more, just so that you've seen some things and you know to go looking for them more if you are interested, or to ping me. This is maybe a little bit more of a stretch for some of you folks in the clean environment, but I guess you're also typically earth science folks as well. So, and the fact that the stratosphere may be cooling because at the same time as the troposphere is warming, maybe makes it relevant to talk about atmosphere layers in whatever you're doing. So this was sort of our approach to the typical layers of the atmosphere, look at a temperature diagram kind of thing, but figured looking at a diagram and then answering some quiz questions is probably not the way to make something memorable. So we tried to make it sort of more of an exploratory thing. So the idea is that you get a few balloon flights. Each balloon can only collect a few data points. We've got altitude along the y-axis, and we've got temperature, or we can switch over to air pressure along the x-axis. And we launch balloons. It gathers data at the points that we indicate here. So we'll get a few data points down low, launch a balloon, and you can see that the temperature is decreasing as we go upward in the troposphere. But if we then launch another balloon and get up into the stratosphere, once we get above the tropopause, the temperature starts warming again because of the ozone up there absorbing ultraviolet. And then we've taken a little bit of artistic license of letting our balloon get up into just to the edge of the mesosphere. So there we're right at the top of the stratosphere. And we can do our last balloon and get a little bit of the mesosphere. So the idea is to kind of mix learning about the content topic with a bit of sort of science practice kind of stuff, of just sort of making the decisions, planning an investigation, analyzing the data kind of side of things. So I think that's a little bit less relevant to most of you folks, or at least the energy side of clean. So I'll move along quickly to a couple other things. Just try and remind myself which ones I wanted to show. Oh, I should definitely pop this up before I go along. So most of the stuff I've been showing so far has been things that we've created, but I've also been kind of collecting almost like a lit review or consumer reports kind of page on just simulations and games from a variety of sources. So some of them are whole collections, like the Annenberg curriculum has a number of things. Some of them are individual items like this BBC Climate Challenge. They're all related to atmospheric science in one way or another because I'm based at NCAR here, but many of them have climate and including energy related aspects. I'll pop into this one from Koshland Science Museum just as a quick example. So they've got this, and because it sort of gets into the energy side of things as well as the climate side, and that's important for clean participants. So this one, they have you start off saying which things are most important to you. So let's say we really care about air quality over cost savings, and we're more concerned about oil independence than land preservation. So you can be sort of, whatever your views are about this to start. And then they have you pick certain technologies or policies to try and improve things across the board, but you've only got, I think, so much money or something to spend on it. So you have to try and make sure that they are most effective on the things that you said mattered to you. And I'm being a little random because I'm trying to talk and do this at the same time. But anyhow, you get the flavor. It's a pretty quick and easy one to get into different viewpoints. It gets very challenging because after you do one round, they move you forward in time, and it gets more and more difficult to meet your goals. So anyhow, that's an interesting one that I thought I'd point out. And just the fact that we've got this collection of a lot of things that are probably relevant to you from all kinds of universities, different nonprofits, NASA, NOAA. Some of them are for sale things like these gizmos by Explore Learning. I didn't want to not exclude things that had a cost just because some people do have the money to pay for that, but most of them are freebies that were developed with your tax dollars or by universities. I think there's one other thing that's, let's see, how can I show that? Where are we at? Oh, I know one other thing I should show. Let me jump back to the PowerPoint quick and jump through a couple other things from other groups, and then I think I should probably wrap it up. There's some real good greenhouse effect items. Let me pull back up my slides, and I've got a few shots of these. I think because the greenhouse effect is such an important part of explaining climate and how it works and why it's changing, these might be of interest to people. And it's, again, one of these difficult things to actually physically simulate in a lab or show how that's working. So I think simulations work quite well for this. The FET collection at University of Colorado has a pretty nice greenhouse effect simulator. I think I've got some stuff that shows aspects of it in the slides. Yeah, so you can go to different time periods where there's different greenhouse gas concentrations. So you can go back to the ice ages where there's fewer greenhouse gases. And I think they've got what, I'm just trying to read it. Oh, okay, and then they've got it so you can just play around with it. You can make it so there's quite a bit. They also have a layer or a level in this where they simulate the greenhouse gases with panes of glass, so sort of taking the greenhouse effect simulation a bit literally, which has pluses and minuses. They also have a thing where you can fire photons across and see how different molecules absorb or don't, depending on their configuration, how certain things are, because of their symmetries and so forth, are greenhouse gases, where other things like nitrogen and oxygen are not and don't interact with infrared. So that's a pretty clever one. Concord Consortium out of Boston also has a nice piece. It's a bit more embedded in some of their curriculum. And actually, let me paste in a URL that will help you find both of these. We made a small unit, we called it a teaching box, that used both of these interactives. So that's probably the easiest way for me to point you at them. So if you go to that teaching box, you can get your way to both of those. And let me get back to the PowerPoint. This Concord Consortium one is pretty cool in that it lets you follow individual either bits of energy or I think some of the greenhouse gases. So you have a bunch of particles. The green particles are greenhouse gases. The yellow things are incoming visible light photons. The outgoing are infrared. And then we've got heat in the ground, and you can spew more greenhouse gases out of the volcano. Yeah, that's the key. But you can turn on this follow feature. So there I started following a yellow visible light photon as it came into the atmosphere from the sun. This one bounced off of the ground and just went back onto space, but then I followed another one. It went into the ground and bounced around as heat for a while till it made it to the surface as infrared. It went up a ways, ran into a greenhouse gas, bounced back down, and then eventually escaped out into space. But you can nicely sort of follow all those steps along the way. They also have a graphing feature where you can kind of do experiments and see how the temperature pops up to a certain new level if you add a bunch of greenhouse gases. So I think,
Randy, one thing I would say is, with there lots of places that do simulations, how valuable it is to have some that you can really count on. NCAR is someone who will relate. You can do things. In the simulation you just showed, I can pick that apart as being scientifically inaccurate. And it's good to have some people that you can talk to if we have each other's back. I would help that people look at stuff we do, and if they see something that's scientifically inaccurate, they talk to us about it, right? And we fix it, right? You want people who are responsive, and we look out for each other because we each come from different experience and different things. I can really pick that one apart that you just showed as inaccurate. I'm not worried that in linking to you that if we have if we can point something out, we're going to fix it. It matters. It matters that we get the science right. And some other folks is like they're just totally unresponsive. You point something out and they just they don't care. So I just when you're looking at that, I guess maybe what I'm doing is applauding your work. I know that we can count on each other to together get things. You know, if we're going to have scientists, we're going to have engineers learn how to take care of global warming and deal with stuff. They can't afford to have it wrong. Right? Your inventions are going to be wrong. Your work is going to be wrong. It isn't just a model is wrong. Your work is going to be wrong. We have to get it right. Anyway,
thank you for that. And it's a tricky business. I think a lot of times groups are, in making these simple models, they're having to be a little rough around the edges on something, but you want to really not promote misconceptions. And it's pretty important to get the science right. It's tricky in the way things are funded too, because often it's like, well, we don't have funding for that project anymore, so going back and fixing things is hard. So
right. And like I would never link. I would never link to it because it's off significantly on fundamentals. And it's one thing to be simple and to not say a lot, but choose what you say, get right. You don't have to say everything, but if you say something and it's dead wrong, that's just wrong, and that I think that exactly, that's it. You want, and cars are round. You aren't this one shot wonder. So if something needs fixing, you go and fix it. So.
Yeah, I think actually, I'm glad you brought that up. I think it would be interesting to have a clean call talking about how to approach places that have stuff wrong. I've had an interesting interaction with the folks at the local Sierra Club who have some serious problems with how they're presenting certain aspects of science, and I'm a little befuddled on how to deal with it. So bouncing around ideas like that would be very helpful.
I don't want to go too much, but Don, I totally support that. I think that discussion is very valuable.
Yeah.
What I could throw into it, and this would definitely go for Sierra Club, is my take is we need the Sierra Club. We need people doing
Right.
things, but I constantly am having conversations with people who overlap with what we do about their science being wrong, and do they care? What I'm getting a lot of is, look, we say we're science education, but that's not really what we're doing. We're actually political. We're politically trying to motivate people to say that global warming is right on their opinion polls. And if we have to get the science wrong to get there faster, that's what we're doing. Okay, I can't stop you from doing that, but I'm a STEM educator. We need to get the science right for the future scientists and engineers. We don't deliberately mess up the science. If you do it, I can't help that, but I'm going to differentiate what we do from what you do.
Yeah, and I'd really love to have that conversation, but I don't want to pirate Randy's time. But maybe Jim, you can stay on for a few minutes afterwards, and I'll touch base with you about what's going on here.
Yeah, I would just chime in that I agree. I think there's a fine line in that, a lot of people have acknowledged that just more knowledge is not enough to get people to take action on climate science. But I think there's a fine line in terms of some people get to be activists without knowledge anymore. And that to me becomes fragile to being manipulated by the next person who comes along who's charismatic and isn't telling the truth, but
Right.
convinces you. Whereas if you have a robust science knowledge, you can say, wait a minute, you don't need to know everything, but I think that balance is important.
Yeah, I will say a tiny bit more in that I think that some of the stuff that's gone on locally here, and this is not National Sierra Club, this is folks in the local chapter, is problematic in that it's obviously wrong to a fair number of people, which I think will make a lot of people tune out what the Sierra Club is saying because they're obviously wrong about some stuff that they're saying pretty loudly. A good topic for a later call.
Mm-hmm. Let me throw one more thing at you guys, and then I think we're pretty much at the end of the hour, and I'll just stop. But this you might find intriguing, and I'll see how far I can get into explaining it. This is another sort of hands-on piece. This is actually originally done by the Little Shop of Physics, which is at Colorado State University, a group that we worked with a fair amount over the past few years. It's sort of a hands-on demonstration of how computer models work, of how the greenhouse effect works, and how the atmosphere is stratified in terms of temperature. And let me just make sure I paste in the URL for this one while I explain it so that anybody can go take a look more in depth later, because this won't quite get the point across, but it's really a neat one. It takes a little time to run through, but shows so many things. The idea is that you've got, do you guys see my pointer on there?
Yes.
Okay, so you've got the sun on the right as this essentially infinite source of these red things that kind of represent photons and kind of represent heat within the system. And then we've got the Earth's surface on the far left, and then a two-layer atmosphere represented by a couple of different sheets. And each of these kind of accumulates these red markers, kind of representing the temperature. So here I think we're at 18 or 20 markers, so it's something like that, degrees. I think we've got the lower atmosphere started off at the same temperature and the upper atmosphere a bit cooler. And each turn you take some of the visible light photons, you take 3 of them from the sun, they pass through the atmosphere and get to the Earth's surface. But also each turn, based on the temperature, and sort of getting back to the Stefan Boltzmann law of, the hotter something is, the more it radiates. These things, the Earth's surface radiates some of its chips away, so they move up towards the atmosphere. But the atmosphere also has a temperature, so it radiates chips. It radiates some of them downward and some of them upward, and the upper atmosphere does the same, some down, some upward. And so you just sort of run this for a number of steps, and gradually the surface warms and the lower atmosphere does, and you eventually get to a point where the upper atmosphere warms enough that it's sending 3 back out, and you've kind of got this equilibrium. But then you can do day-night cycles, you can do seasonal cycles, you can sort of show how the spin up of a model works, that even if you start with some weird configuration with the upper atmosphere a lot warmer, that it'll eventually, because of the rules in the system, come to a reasonable equilibrium state. So anyhow, I've got the write-up from that on the page that I pasted in there, and I've got some videos that kind of show time lapse of this, because it takes like 20 or 30 turns of moving all these things to get to some of the equilibrium. But anyhow, I thought that was a pretty clever and nice mix of sort of the hands-on stuff. And I thought that was a good stopping point. So I'll stop there, and And thank you all for coming.
Yeah, thanks. Great.
Thank you.
Time for a few more questions if folks want to throw them out there.
I will just mention we're definitely very interested in partnering with people who might have interest in these kind of things. We're interested in disseminating to teachers, but we're also interested in looking for research partners who might help us find a way to fund studies of this, but also that notion of the connection between the simulations and the physical stuff that Jim was raising is certainly of interest too.
Yeah, and as I mentioned, we're very interested in we're working on this new museum exhibit that we'd like to have some features of that in it, so we should definitely talk some more.
Yeah, definitely would be.
And Randy, to back it up, I mean, if we take specifics or go into it, it is possible. We would all know that you can simulate something, and it can be quite unscientifically, it works, right? I mean, it looks there, but It doesn't have anything to do with the reality. When you do things in a physical demonstration, that's less like it. You can screw that up too, but it's harder to. You have to be on your game a lot more, because it's got to work. And there's a lot of other factors that have to be safe and has to be exciting, but it has to function, or it's a crappy demonstration or a lab. That then can feed back to why the simulations that are good, right? Because we can back up in physical reality what your demonstrations do. The demonstration you showed me before, where I could pick apart, we can do demonstrations to demonstrate why it is wrong. I can demonstrate for people physically why their way they depicted how the greenhouse effect works does not correspond with reality. It is way off. And so it can really back you up, right? Which helps. It helps getting funding for you. It helps the public appreciate that your things are right. It gives people all these different types of way of learning and things. But I would just back up that that's part of what we do, is we can confirm the reality or the non-reality of a simulation in the physical world, and that's pretty exciting.
Yeah, I like that angle on it, because I usually think of it as an educator of how does it make the point, and often it's, well, we can do this physical demonstration that it makes the point well, that the thing that's in the computer simulation is believable to somebody, but having it actually be valid as part of that is a key element. So that's, I like that.
All right. Well, it's 2:00, so I thought it was great. Thank you very much, and I hope to catch up with you and pick your brain about our exhibit.
Cool. Yeah, looking forward to chatting with you about that. And yeah, thanks again, folks.
Thank you, Randy.
Thanks, Randy.
And color one is Jim.
I'll hold on, and we know that the thing's going to shut off, but I think we can still talk. So.
Right, and it won't actually shut off because I'm
okay. You're in control. Yeah, great.
I will stop the recording.
Thanks for jumping in and helping out, Don.